Great. So, it's my pleasure to introduce Erhard Rahm, who had a pretty hairy travel last night. His wallet got stolen in the train in Germany, including ID and things like that, but he made it onto the last flight, arrived 1:30 in the morning. So I think, great to have you here, Erhard. I've been working with Erhard for like the last 2 years or so. Erhard is a professor in computer science and leader of the database group at the University of Leipzig. He's done a lot of work in data integration, schema matching, record linkage, entity resolution. He has a very very good track record. He has several what are they called again? Best paper awards and test of time awards in VLDB and ICDE. So a very good. Sorry, I had enough coffee this morning. A very good record in not record linkage as well, but also coming up with ideas which over time have shown to be influential in the area. So over to you, Adam.
Okay, thank you, Peter, for the introduction. And yes, good morning, everybody. I'm very happy to be here. And sorry that I'm very late. Missed many interesting presentations, but I will be here for the rest of the week. So I'm looking forward to the remaining presentations and the discussions. So in my talk this morning, I'd like to discuss a little bit about data integration work that we did in the past and that we're currently doing, which is also related to big data. And this work that we're currently doing is done within a new center for big data that we're doing together with the Technical University of Dresden. And this center is called SCATS, which stands for Competence Center for Scalable Data Services and Solutions, Dresden, Leipzig. So a few years ago, the German Ministry for Research and Education basically wanted to establish two centers of excellence for big data in Germany. And there was a competition going on, and finally the two centers are in Berlin here and in Saxony, Leipzig, together with Dresden. So the whole thing started 2 years ago, and the initial funding is for 4 years, and we can have 3 more years funding if we have been successful. So in our center, so we are doing research on different topics. So one topic is data integration and data quality that I will also touch on today. We also have professors and colleagues working on knowledge extraction and of course machine learning and especially visual analytics. So we have to visualize also the results to make it understandable for the scientists, for the users. And we also have some broader topics about big data architectures or the life cycle management of the data and support for workflows. So, and we try to apply now results from these different areas now in different application domains. So we have in Dresden and Leipzig experts for life science research, bioinformatics, and material engineering sciences, environment, geosciences. Digital humanities is also strong in Leipzig, and we also look into commercial applications. And we also have a service center that tries to connect now the different areas and the application scientists with computer scientists and to also provide support for companies who are interested to work with us. Okay, so within this center we are doing also, as I mentioned, data integration work. And I don't know how much has been said already about big data, especially in this workshop, but you probably know about these general big data challenges which are associated with different V features. So one V is for volume. So obviously we have to deal with high data volumes, and we're not longer in the gigabyte or terabyte range, but oftentimes we have petabytes. For example, if you look into web data or data from social networks. And the standard architectures of data management have problems to deal with petabyte in the petabyte data range. So we need parallel clusters and all kind of high-end infrastructures to analyze this amount of data. So the next V features velocity. So we often have data streams, quickly changing data, for example, in social networks like Twitter or if somebody wants to intrude your computer system, you should really observe this very quickly, that you are able to react to these problems in a short amount of time. And what is more related to data integration is variety. So we have different kinds of data, structured data, semi-structured data, unstructured data, and of course we have also many data sources that we want to utilize and take the data from and integrate the data from and enrich the data and analyze the data in a better way. And the next feature is veracity. So we really want to have trustworthy data, so we really have to ensure that the data is of good quality, which is especially a problem for web data, for data from social networks, etc. So we have to invest a lot to improve the data quality. And finally, obviously, all these things have to provide a value for the users and the scientists or the commercial, the companies, etc. So nobody really invests so much into the whole big data life cycle without having a clear picture of what is needed and what are expected results from that. Okay, so typically we have a data analysis pipeline or data management and analysis pipeline. So we have to get the data from different sources, and we have to invest in pre-processing to ensure good data quality. We have to extract some features from unstructured or semi-structured data. We have to transform the data. We have to clean up the data, consolidate the data. Finally, we have to integrate the data from different sources, or we may have to enrich the data with annotations. And then after this, we are basically in possible basically to analyze the data and finally visualize it and make it accessible for the user. So this is not really a new pipeline. So for example, if you're looking into classical architectures like data warehousing, you have very similar steps, but in combination with these challenges I just mentioned, these are much more challenging issues now. So here I guess I have mentioned it again, so heterogeneities, variety, volume, velocity, privacy also of course is a topic. If you have sensitive data, person-related data, this has already been covered I think at this workshop. And also if you have to basically you have to also have a good connection to the people to use the data. You have also collaborative approaches that come into play here. So this is a bigger picture, and we are more interested here in the green steps about data extraction, cleaning, and data integration. So these are the main steps that are basically here of interest. So data integration in general, you can have roughly two levels. For one level is the metadata level, for example schema or ontology level. So you may have in the simplest case two different data sources which have their own schemas describing the structure and the meaning of the data. So basically you have to align these different schemas to identify now corresponding elements like for example corresponding attributes in schemas or corresponding concepts in ontologies. So this is a task of schema matching. And in some cases you not only want to have now these connections between the schemas, but you may actually want to combine the metadata into a unified metadata model, a unified schema or a unified ontology. Then you have to somehow merge these different models. So this is of course more complex than just matching. So matching is typically the first step you have to do for merging, and then you know what should be really be combined now in the integrated model. And then the remaining parts obviously should also be included in the integrated result to not avoid any information, not have any information loss. Okay, and then we have the instance level or the entity level or object level, whatever we want to call it. So there's the real data basically, which basically is in this case we have to do the pipeline just mentioned. So we have to do this transformation of heterogeneous entities in a uniform representation. We may have to resolve some data quality problems, and we also have a matching step here. So we have to identify equivalent instance records, and then basically this is called object matching entity resolution. And the linked data world, people talk about link discovery. So this is analogous to the schema matching problem, but now we have to deal with many more objects, and In some cases, we also actually want to do a merging or a fusion of the matching objects to combine the information from different representations. So basically to also enrich or augment now the entity description. Okay, so this is a high-level view of the two levels of data integration, and related to big data is the four key challenges that we have to address. Obviously, we have to deal with a very large data volume, so we have to do large-scale matching. And one step obviously is to have to avoid now for matching to compare each entity with each entity. So we have to apply so-called blocking techniques to reduce the search space, and we also have to, in addition, apply massively parallel processing at different levels. So each server has, of course, many processors, many cores that can be used in parallel. Then we have clusters of different servers, and we can also have graphic processors, GPUs, for example. So typically we have to apply different levels of parallelism to speed up the whole computation, especially also for matching. So I will talk about this later. The next thing I call holistic data integration. So most data integration approaches just look at two sources at a time. So they do just pairwise matching, which is of course a good starting point, or basically a building block in all these data integration solutions. But what we really need in many cases is to have a more holistic approach that basically is able to combine information from many data sources, let's say hundreds or even thousands of data sources. And then if you do pairwise matching, then we basically have a scalability problem. So as you can easily find out, if you have, let's say, 20 data sources and you want to do a pairwise matching among all these sources, then you have 19 times 10 mappings to determine, which is 190. And if you have 200 sources, we are already talking about 20,000 mappings. And with current tools, you really have a problem to determine 20,000 mappings and maintain 20,000 mappings. So basically what we need here is a more clustering-based approach that will really determine now clusters of matching objects, and these are better to maintain, incrementally update, etc. So I will talk about such a clustering scheme later. So third problem is data quality, obviously, as I mentioned already. So we have these different kind of data sources. We have to, of course, the more data sources you have, the more diverse the data sources are, the more you have to invest into data cleaning and data enrichment, which is really a nasty topic, or really difficult topic. And finally, privacy I mentioned already. So we need privacy preserving record linkage and privacy preserving data mining. So I won't talk about this. We also did some work in this area, but this is already well covered, I think, here at the workshop in other talks. So I won't talk about the last topic, but I will touch on the other ones. Okay, so in the rest of the talk, I first like to talk a little bit about scalable entity resolution. So what we did is we actually analyzed the existing tools and frameworks a couple of years ago for entity resolution and also for link discovery, and observed, of course, certain limitations. And then we applied more holistic approaches for matching product offers from different web shops. And we also implemented a Hadoop-based tool for entity resolution called dedupe. And this includes also techniques for load balancing to deal with data skew, to really be able to utilize different machines now in a good way. So in the second part, I'd like also to talk a little bit more about this holistic data integration idea and different use cases that can make use of such an approach. Okay, so just to, I can go over this very quickly. So in the standard world, you have basically the data in different tables, for example, about customers, and you want to find out the matching customers for object matching or entity resolution. So here, even the simple example, you have a schema matching problem. So in this table, you have a name attribute. Here you have split last name, first name. So basically the color indicates already the matches here. And here we have gender, we have sex, different representations that have to be harmonized. Here we have one attribute. Here we have split it into street and city, etc. So even here it's not trivial really to find out, for example, for frequent last names like Smith, who are really the matching customers. So typically we have to combine information from several attributes, and of course there is no exact matching, but typically you need some approximate matching for all these attributes. For example, here we have Kristen, we have Chris here, and so on. But basically you have to combine the similarities from different attributes and to have a match decision derived from these similarities. So in the web world, things are more complex or more less clean, so we have to extract the data. For example, here Google Scholar, as you all know, does actually a very good data integration already. It's not perfect, obviously, as we see here, but it's already very good because they really are able to do such a holistic data integration I mentioned. So basically they collect now publications from, let's say, thousands or even millions of websites. They get the data from publishers and combine now all the records about the same publications within clusters. So basically here we have a cluster about our data cleaning survey paper, which is 37 versions that they found somewhere on different websites. And there are also cluster, obviously, the references that appear now in the reference section of the papers now to collect now the citations. So this is only one cluster, basically. Basically, this is holistic integration already. It's not perfect, as we see here. There are other similar clusters. So basically, these clusters should really be combined. So this is what you have to do if you take care of these issues in your Google Scholar profile. So it's not really the complete list. So you see, so there are extraction errors with the name, etc., and with the title. Maybe he has only problems in current approaches, and so they confuse in some cases title and the author names, etc. So anyway, so but in principle, that is, I think, is the way to go to having such a clustering-based approaches, and to of course to aim at a high quality here. So, but normally, if you look only at one or two data sources, the classical workflow for object matching is, for example, for two data sources, you basically want to determine now the correspondences, so from the subset of the Cartesian product, but you don't want to evaluate the complete Cartesian product, so you do some blocking step first. Normally, unless you have very small data sources, in this case you don't need that, but normally for bigger data sources you need a blocking step. And then you do the real matching, so you compute now the similarities, for example, attribute similarities, and then you need a match classification, or you have to determine now the real matches. Even you can use a learning-based approach based on training data, or you can have some rule-based approach. So there are different possibilities here for finding out likely matches. So this is normally the result here. So having a set of correspondence. Optionally, you can actually try now to get additional indirect or transitive matches by determining now, let's say, connected components or transitive closures, and this also gives us already some kind of clustering. So you see, clustering is also possible here with this classical approaches by this post-processing here. And there are different cases here. Of course, it's better if you have clean data sources. Then in the best case, you have only to have a one-to-one mapping here. So each record here in the first data source matches at most with one record in the second data sources. So this is the best case, basically. Otherwise, you have duplicates within the input sources. Then you have one-to-n or n-to-m mappings, which is are more difficult to deal with. So typically, it's a good idea to really clean up your data sources at first, to eliminate duplicates within data sources before you really try to match with other data sources. Okay, so this workflow is basically followed in many existing tools, and a couple of years ago we analyzed more than 10 of these tools that utilize learning. So they try to have this match classification model basically built or learned from training data, so from pairs where the match decision is known. So typically this is based on SVM or decision tree learning. So in principle, so all these tools have these different kinds of blocking approaches, mostly attribute level matching for relational sources. Blocking is mostly based on manual decisions for the blocking key, etc. So the evaluations are also non-conclusive in most cases. So we also did some kind of comparative evaluation of different learning and non-learning approaches for different match tasks from the bibliographic domain and also from e-commerce data about product offers. And we observed that the learning-based approaches are typically better in match quality than the rule-based approaches, because at least especially for the more complex situations for e-commerce, for example, where you have to consider different attributes to get a good match decision. And it's really hard for experts to come up now with good thresholds, for example, for similarities and how to combine with different weights for the different attribute similarities. So this can be actually better done by learning-based approaches, provided you have good training data or enough training data. But these learning-based approaches also tended to be slower than the other ones. So there's a need for performance improvement, especially for the learning-based approaches. So more recently, we looked into so-called link discovery frameworks from the Web of Data or linked data community, so the semantic web community. So we again, in this recent survey, we also considered more than 10 different tools. So some of them also do some ontology matching, plus also this entity matching or link discovery, and some of them are learning-based, and there's also some of them participated in a competition, but still the relative performance is quite unclear at this point. So I don't want to go into the details of these different tools, so there are also all kinds of limitations. So, but of course all these tools do really only pairwise matching, so there's no real tool that supports this holistic matching, which is actually needed in my view, especially also for this linked data situation. So I will later discuss a little bit this holistic data integration for the semantic web environment. Okay, let's now come to our use case about matching product offers from different web shops. For example, this is needed if you want to build up a comparison portal, and this would be a typically big data integration use case. So we have now these product offers like for camcorders, for example, in many shops, in many data sources. And if we have, of course, many product types, not only camcorders, in principle we have millions of products and product offers, and these prices especially change continuously. We have many similar but different products, so it's not really easy to determine the real matches. So for example, here for these camcorders, you see here Canon Vixia HF-S10 is here 3 times. Here we have S100. So one character more, 1 0 more basically is a different model, which is of course a different product. So you should not really have a string similarity. The string similarity would be pretty good, but still we have a different, completely different product. And here we also have this Vixia something HF-S10 here, but we don't have a camcorder here, but some accessory product, and we have to of course distinguish accessory products from the real products. So this already indicates that it's not so easy really to find out. Basically we have to extract now from these names of the product now interesting subsets which are suitable for matching, for example the manufacturer, or also these product types. So this should be extracted, which is doable for electronic products, but not of course for all kinds of product types. So we have to find out what are the relevant features, and that should be provided or extracted and cleaned up for matching. Okay, so in our approach that we developed, we have as input now many new product offers that continuously come, and we also basically do not only try to match offers with each other, but also match with an existing product catalog where we basically have already product descriptions and previously assigned product offers. So basically we can then match now new product offers to already existing product offers, which makes the problem a little bit easier. So we first have to do this pre-processing or data cleaning. So we have to extract relevant features, for example manufacturer information. Of course, as you can imagine, there are many variations how the manufacturer names are now spelled and abbreviations, etc. So we have to consolidate this with some background knowledge, and we also extract now for electronic products product codes, having some regular expressions and other techniques, And then basically we try for each product offer to find out what is the product type of this product offer. We don't want to compare each product offer with all kinds of products, but we only want to limit this to the specific product type. So we apply some learning-based categorization for product offers. And then only within the product type, basically we compare now the product offers, which is again based on a learning-based model per product category. For each product category we learn a separate match model, and then we use this after we have determined the product type to basically now compare a specific product offer with other product offers of this type. Okay, so here's the overview. So the pre-processing, product code extraction, manufacturer extraction and cleaning, and the categorization of the product offers. And we have to learn the model here first with training data, and then we get the classifier model, and then we apply this model now. Okay, we also apply blocking on manufacturer and category, we determine the similarity values, and basically in the classification model we find out the final matches. So this works pretty well in most cases, but it was also rather slow, so we had to think about performance. So so this was done already a couple of years ago, and so we applied MapReduce from Hadoop now to speed up this whole process, or this entity resolutions workflow in general. So this is actually easily possible, with MapReduce. So this is a core workflow: blocking, similarity computation, match classification. So if you have map and reduce, with one map and reduce job, you can actually do blocking plus matching. So for blocking, basically you can use this map phase on the input records. So basically you have to determine, of course, the blocking key if you use standard blocking. So let's say you want to do on product types the blocking. So basically for each input record you have the product type information. Then basically you extract this product type or manufacture whatever you want, and each color here or each symbol basically means the same blocking key. So basically, and then after this mapping there is a repartitioning of the data based on this key, and basically all records for the same blocking key go to the same reducer or the same node in this parallel system. And so basically you see here all the records from this type are here, and here all these records from the second type, and so on. And basically each block basically ends up in the same computer and can then be matched within this computer in parallel to all the other matching that's going on for the other blocks. So this matching basically is then done in parallel for different blocks. So this works pretty well as long as you have not big differences in the block sizes, which is of course typically the case. So basically you have to think about load balancing issues, because as you can imagine, some product types are much more common than other product types, and also manufacturers differ a lot in the number of products they manufacture and provide, etc. So we have to deal with these imbalances now regarding blocking sizes. So we applied load balancing techniques to tackle this problem. To make good use of the parallel infrastructure. So in principle what we do is we need, of course, information about the block sizes to do some optimization. So we apply additional MapReduce job to analyze basically in the first phase the block sizes, so the blocking key distribution, the number and the size of the blocks. And basically the goal is then for load balancing to split basically big blocks into smaller portions that can be matched now in parallel. So one approach called block split basically leaves the small blocks as they are, and so they are basically matched completely on one node, but the big blocks basically that would result in overloading single node are split into sub blocks, and we then determine multiple match tasks for these sub blocks that can be better balanced now among the different nodes. So this can be easily illustrated for an extremely simple example. So let's assume we have 3 smartwatches in one block and 6 cell phones or smartphones in the second block. So there's just two product types, and basically an easy calculation is in this case we have 18 pairs to compute within the two blocks, which was assume one time unit. And if you do a parallel matching on two nodes, then we get a load balancing problem here. So we have okay, this problem is my animation here. Okay, here's the two blocks basically. Okay, and with a naive approach, we would have 3 pairs to compute for the small block and 15 pairs for the bigger block. So basically, we have here an imbalance, obviously, in the load of the two nodes. So basically, the speed up would be, okay, here we need this, basically, is the dominant execution part here, 15 pairs to compute. So in one node, we have 18 pairs. Here we have 15 pairs runtime, basically. So the speed up would just be 18 over 15, is only 20% improvement compared to the one node case. So basically, now we have to split up this bigger block here. So basically, let's say we split it up in this way. So in the green and in the blue sub portion, and then, okay, here we have 3 comparisons. We do nothing about the small block, and here we have the split. So we have now, of course, to match the green ones with the blue ones, and the blue ones with themselves, and the green one with themselves. So we have 3 match tasks for the bigger block here, and we split now these 3 match tasks among the 2 nodes, as you see here. So the pre-processing, we have actually found out how to split such bigger blocks. So basically, in this case, we would have here 2 comparisons. Is this correct? Or is it only 1? Then 2 basically means, okay, only 1 comparison here, and 2 to 4. Okay, here's the computation. So we have 3 pairs here. We have here 4, 6 pairs, and here we have 1 pair, and here we have 8 pairs. So altogether we have 9 pairs here and 9 pairs here. So we have a perfect speed up of 2 after this block split. So in a similar way, we can of course deal with many more blocks and bigger blocks, etc. And we analyzed this and on Amazon infrastructure, and so we achieved near linear speed up with this load balancing. So the execution time on one node was about more than 20 hours, and it went down to a few minutes, and the speed up was for 60 nodes 50, and for 100 nodes it was of course not a big improvement anymore for relatively small data size. So we have a little bit more than 70 for 100 nodes, but in principle it's scaled very well here. And this has been implemented within our dedupe tool, which stands for deduplication based on Hadoop. So we have this MapReduce based approach implemented. We have a powerful library for blocking alternatives, not only standard blocking, but also sorted neighborhood and other techniques. We also have different match approaches based on learning or without learning. And basically the user can specify the methods and the possibilities with the GUI, and the MapReduce jobs are automatically generated, and the load balancing is applied, and optionally we can also have this transitive closure computation to get some clusters from these correspondences. Okay, so that ends this first part. So okay, now a little bit of a time problem. Okay, let's now look into this holistic data integration a little bit. So as I mentioned in the beginning, we have a problem if you have many data sources. This is pairwise matching. For 200 sources, we have about almost 20,000 mappings to determine, and we have of course to deal with many data sources with this linked data environment. We have many web shops, as I mentioned. So basically what I mentioned, the Google Scholar case and also this product matching, actually were already some holistic data integration use cases. And also an interesting use case is people have extracted tables from web pages. So they have found millions of such tables, and the question is, how can we really make use of these many tables? Can we integrate this information in some way, or can we enrich it for queries, etc.? So this is an interesting use case for data integration, data analysis, which has this holistic flavor, but it's extremely challenging to really make use of these huge data collections. And there are other repositories for open data where thousands and millions of files of all different domains are basically collected. The question is, can we really make use of this collected information? So actually 2 weeks ago I had a keynote at the ATBIS conference about this holistic data integration, and I have actually also written a paper in this lecture notes, so for the details of the coming things you can find here more in this paper. Okay, so I have basically analyzed 6 different use cases. So an old use case has been basically if you go into the deep web, basically you have web forms basically to post queries on underlying databases, and the idea is to have now the possibility to have a meta search about different sources. So basically in this case you have to come up with a mediated schema, which is basically typically based on a clustering of the forms or the schemas of the individual sites. So this is the idea behind this mediated web query approach, which is in a way a virtual data integration approach. That is, the data is not physically combined, but it remains in the underlying data sources, in the hidden databases basically. So you pose a query here, and this query is basically now goes now to the data sources where it is executed the query, and the results come back and are provided to the user. So this integrated or mediated schema basically is based on a clustering of the attributes. It was relatively simple techniques that have been developed about 15 years ago. This was this research. So we have the schema is extremely simple, a few attributes, often very similar names. So this was a relatively simple case. The next thing, this open data repository is much more challenging. We have up to millions of tables or files in these repositories or extractions from the web. And the integration so far has been extremely limited. So in some cases people try to categorize now the different tables or files by domain to make a little bit better to or easier to find out or to find relevant files. So and then you can try within the domain to identify similar tables, similar attributes within tables, and maybe to have one table and expand the table with attributes that are missing in one table by relevant attributes from other tables. So there have been a few dozens of papers now in the last 5 to 6 years about these techniques, but still this is quite limited and there is much potential for more research here. So the other use case for this is basically mostly metadata oriented, and another use case related to metadata is integrating now related ontologies, for example in the life sciences. So UMLS is one example. So basically dozens of different life science ontologies are physically combined in one integrated ontology here, and so basically there's also a clustering at the concept level. So synonymous concepts are basically combined in so-called synsets. But this is pretty good in the quality, but it depends to a large degree on manual experts or on experts, curators. So we have to do a manual integration here to get a good result. So this is a good thing to have and to do, but it's not as automatic and therefore not as scalable as one would like to have it. So more scalability is possible if you go at the instance level, at the entity level. For example, the Google approaches, Google Scholar or the Google Shopping basically have this clustering of matching entities, publications, product offers. So we have here physical data integration and can really support thousands of data sources. Then of course it's easier if you have simple data entities like publications, which have a relatively simple structure. Product offers are more diverse, so it's more complicated. But in principle, this is, I think, a good way to follow. And if you go to comparison of booking portals, we have similar approaches here. And we can also cluster the offers often within some taxonomy, for example, per product type or per region, if you have, let's say, hotel bookings, etc. So basically, you have mostly instance level matching, but also associated with some metadata structure. In most cases, you have physical data integration, but if you have really, if you want to have the most recent price or the most recent occupancy for hotels, you might also have a little bit of a virtual data integration to look up now, finally, as the respective data source, what is the current price, what is the current, is there really a remaining seat in the flight, etc. So, and finally, what is also very interesting are so-called knowledge graphs. So this was an idea that came up in this linked, this semantic web. So DBpedia was extracted from Wikipedia. So you have from diverse domains now entities that are basically collected and also combined if you have information from other data sources as well. And Google and other big players now in the web search have also now developed huge knowledge graphs to enrich now the web search. So they have background knowledge collected in these knowledge graphs that can be used now to enrich web queries. So we have a large-scale collection of entities from different domains, and they basically also extract data from queries from websites, and they use also Wikipedia and other data sources to combine this knowledge about specific entities, about persons, about movies, about everything basically, about locations, about universities, etc. So it's extremely challenging and scalable. It has to be scalable, but it also has lots of data quality issues. So even Google basically does it not completely automatically, but really relies on manual experts, curators, to keep the quality at a good level or get relatively good quality. It's not perfect, but relatively good. So as you know, if you go to Google and do a web search, for example, Leipzig University, you do not really have to go to Wikipedia anymore. You get the information, at least certain information already on the right side of your web result. So you see Leipzig University is not as old as Cambridge University, but still was founded in 1409, so more than 600 years ago. And we have alumni like Leibniz, which was at the same time then Newton, and also more recently Angela Merkel and others. Okay, so in this table I have compared the different use cases. So we have mostly physical data integration in the lower part for the last three use cases. Actually, the first one was more or less virtual, otherwise we have mostly physical data integration. Here we have in the beginning more metadata oriented approaches. Here in the second part it was more instance level, but also in some cases combined with metadata, for example taxonomies. Here also the knowledge graphs have a taxonomy where they basically now map all the entities to, so we have persons, geographical entities, etc. And so okay, we have here attribute clustering, concept clustering, in the other case more entity clusters. And the degree of automation is different, the number of sources is different. Often we have only one domain in the knowledge graphs, we have many domains. Also with open data, we have typically many domains. So we have very challenging areas here, especially for open data and knowledge graphs, where many problems are still to be solved in my view. Okay, so let me, okay, these are the observations I mentioned already. So I think it's good to have clusters instead of mappings. So a cluster of k matching objects basically represents k square over 2 correspondences. So cluster size is limited by number of sources. If you have duplicate-free sources, or at most one entity per source, and it simplifies the fusion of corresponding objects, these clusters, and it's easy to incrementally add now new entities or new data sources. You have already a set of clusters, let's say product offers that are already combined, then you get new offers, then you basically now incrementally match now with the clusters, not with all other data sources. And then you can directly now enrich now the clusters and combine the information. So basically clustering based approach has many advantages here. Okay, so we looked a little bit more now in this holistic entity resolution, this clustering approaches to get to scalability, the possibility to dynamically add now sources and entities. We also have to support not only one entity type. Many other approaches only look in one entity type, only publications, only customers, etc. So in the web world, we have many product types. We have also in the semantic web, we have, for example, in the geographic domain, we have mountains, we have cities, we have lakes, etc. So we should really distinguish the different entity types. So we also determine per cluster a so-called cluster representative for further matching. So we do not want to match new entities with all members of the clusters, but only with this cluster representative to reduce the match effort. Okay, so these are basically the ideas. So this is shown here. So we have basically then for each entity type have a set of clusters, and here the bigger bubbles here basically are the cluster representatives. So when there are new entities coming up, we have to basically so for different data sources. So there might be entities of different types now per data source. and they can now basically we have to first, this is not shown here, in the pre-processing we have to find out the entity type. So this, for this product example, we had to do this learning-based approaches to determine the product type per offer, and then basically the color basically indicates now the entity type. And if we have found out the entity type, then of course we only go to the clusters of the specific entity type and match only with the cluster representatives of the specific entity type. So this is a rough, the high-level idea how we can implement such a cluster-based approach. So basically in the beginning, if you have the first data source, you can just take each entity in the first data source as a cluster, and then in the second data source we match now per entity type only with these one entity clusters, and then we increase the clusters, etc., and then we can additionally bring up now new data sources and further entities. So this is not done in this linked data world, so you probably have all seen this picture with, so I have to yeah, okay. I started a little bit late, I think, but but it's fine. I can come to the end very quickly. So here we have typically in this linked data world only these binary mappings, which are so-called same as links. So basically indicating now the matching entities, matching concepts now in the different data sources. So here we have also indicated by color different domains now by these different data sources. Wikipedia is a multi-domain data source which is highly connected to many other data sources. So we have typically a virtual data integration in this environment. So people have really to find out, okay, what data sources could be relevant for my query, and then they have to use Sparkle query language now to formulate the query, and they have to traverse these hopefully existing links to access the data and combine the data within the query from different sources. So this is an extremely cumbersome approach and error prone, and basically depending on good quality mappings, and in fact many entities are not connected to other data sources, so the coverage of these links are pretty low, and so basically it's really has many problems now for data integration. And on the other hand, virtual data integration is inherently slow and not scalable, because the runtime basically depends on how many data sources you basically have to access, and the slowest data source basically determines the overall runtime. So in principle, I believe this is not a very scalable approach for big data-like requirements. So people do this, but I would be, I think a more physical data integration using more clustering-based approaches would be very interesting. And this can be actually, it's not a one or basically can be combined, the two approaches. This can be left as it is, but in these hub data sources like Wikipedia, you could also now add now clusters of entities, of combined entities now from the other data sources to enrich now this knowledge graph in a way to make the information more readily available. So, and we have actually now in our recent work implemented an approach for such a clustering-based or holistic entity resolution for linked data. So what we actually also want to utilize, there are already existing links, and we want to, of course, take into consideration these existing links, but of course combine these connected entities in clusters and improve the clusters so that we have really good quality clusters, and that can be used as a basis for further data integration. So in our workflow, basically, we have as an input existing links between different data sources. For example, in the geographic domains, we have links between these data sources, and we use these as a starting point. We do a pre-processing. We have basically to find out the entity types. We have to also harmonize the entity types, and per entity type we do this clustering. Then we do initially the connected components, but then of course the connected components are not really very good quality in all cases, so we have to really check now each existing connected component whether all members are really matching. So we do this additional checks, and we have to basically split in many cases the clusters to get good quality clusters, and finally we may also have to do a merging now of these split clusters to find out further matches, and this gives us then the final result. So this is a very promising approach. I don't have the time to go into too many details. So one problem we found out is that the existing links do often ignore the entity type. So for example, there is an existing link for Lake Louise. Lake Louise is a nice lake in the Rocky Mountains in Canada, but there's also a city called Lake Louise, and if you look at the geographical coordinates and the name, of course you have a very good similarity between the two Lake Louises, and you really have to find out, okay, is this really the lake or is it the city? And existing tools do not really take this into consideration. So they really assume, okay, Lake Louise is a lake, but if you not really look into this issue, you really have a wrong link. And so really have to distinguish or find out in the first place, what is the entity type here? And that is really, the existing links are okay in many cases, but in some cases are really wrong. And we have to also find out or have to deal with these problems in our workflow. So, so this is just an example we used in our paper. So we have now initial links here, which are indicated here, and we have now the different data sources. And one problem is that the entity type is not existing in some data sources, like New York Times. But in other ones, of course, we have completely different entity types. So we have here settlement, body of water. We have here settlement, okay, we have mountain, or basically what is here? Okay, we have lake, body of water. Here you see already the differences. So basically, and we have to do a manual harmonization of all these entity types in the first place to really be able now to do some kind of matching. So what we did here is, so this was the beginning, and then we did some kind of harmonization with background knowledge, with which our own manual work actually. So basically we have now for Lake Louise in some cases body of water, in other cases settlement, and obviously we should not really match now the two different entity types. So this is basically a pre-processing step to do this harmonization of the entity types, but we still have a problem with these unknown entity types in some cases, and we have to use some heuristics, so based on locality, geographic proximity, and also the name similarity. But in principle, it would be necessary to have this entity type also. Okay, I don't want to go into too many details. So we have now this workflow as I mentioned. So okay, I think I have to skip now the details. If you're really interested in this, I can give you a paper which is under review at the moment. But okay, so let's come to the end. So I think I have covered a little bit big data integration. So we have now the requirements of variety and veracity, which are related to data integration, also of course volume. We need actually, which is often ignored, intensive pre-processing and data cleaning to get good data quality. Blocking is of course important, plus parallel matching. And learning-based approaches are very promising. And what is interesting to me is this holistic data integration direction, to be able to combine information not only from a few data sources but from many data sources. And there are many existing challenges, especially for these building up knowledge graphs or making use of such corpora of tables and other data sets. Okay, so thank you, and looking for your questions.
Thank you very much for a very broad talk, which basically shows that record link is not just limited to linking people. There's many more problems out there. So, questions? It's early in the morning. Do you know more about?
Yeah.
You said that the approach works if you have duplicate-free sources, and back in the beginning you said that you do data cleaning and enrichment. So is the act of data cleaning trying to identify those duplicates?
Well, I did not, in this workflow, I did not differentiate now the data set specific deduplication. So this would be still a part of the data integration step. So data cleaning, I mentioned, we have to harmonize now, let's say, the gender representations and that stuff. So, but if you have both steps together, data cleaning and data integration, okay, you have maybe 5 to 10 different sub-steps, and one of them would be this deduplication within one data sources. Of course, if you have one clean data source and the other one is not clean, and of course you have the one-to-n mapping, of course you can also use this to deduplicate the other data sources. So all the n records that go to the same data record now in the clean data source obviously should be candidates for duplicates. So this could be used also for deduplication, the other data source, but there are other possibilities as well. So But I did not differentiate at this level, this separate step, but it would make sense. And did you have a second question or no? Okay. Yes.
It's all about English. What do you do with the language factor?
Yeah, that's of course one of the other challenges I didn't mention. Though we actually do also this kind of ontology matching, and UMLS is mostly in English, so this integrated ontology. But they also have now, if you look at other anatomy ontologies in German, other languages, you may have to translate basically the German vocabulary to English, and then of course you will lose some information. But this is one way people go. But it's yeah, the similarities are different maybe. In some cases, string similarities etc. work also in other languages, but this is not so well explored, of course, as for English. So there are of course many opportunities also for multilingual data integration approaches. So this is an important thing to consider.
Yeah, I just wanted to thank you for your algorithm for parallel pair generation. I implemented it in Python. It's incredibly efficient, and on my blog if people want to use it in Python. I really like it.
Thank you.
Right, excellent. Okay, let's
All right.
again, and then we'll move on.